Hello everyone, I am Surendra, Master Teacher of Mathematics in Vedantu. In my weekly sessions on ISI and CMI preparation, today I am discussing CMI 2022 Part B of 23rd May. Last week I discussed Part A of the same paper, and earlier we have discussed 22nd May 2022 paper also. Actually, this year CMI has taken two papers. Okay, so let us discuss these questions one by one. First question is, let n is equal to curly bracket 1 2 3 4 5 6 7 8 9 and l equal to a comma b comma c. Suppose we arrange 12 elements of L union n in a line such that no two of the three letters occur consecutively. If the order of the letters among themselves does not matter, find the number of such arrangements. Okay, so for this first part I will do it in two ways. Number one, that because we want no two letters is consecutive, so here I will be first arranging these single digits 1 2 3 up to 9, and that arrangement will be done in 9 factorial ways. In 9 factorial, what I am doing, I am just arranging 1 2 3 4 5 6 7 8 9 at these 9 places. All these numbers 2 4 1 7 6 3 5 and 9 and 8, this arrangement I am doing in 9 factorial ways. Now, as we want no two letters should be together, so we will be finding gaps, we will be finding places for these ABC out of these 10 gaps. One on the left hand side, one on the right hand side, and in between 8. So if these are 9 places, so we will be getting total number of 10 gaps. Among them we need only 3 gaps. So we will be then finding 3 gaps in 10C 3 ways. And then in these 3 gaps we will be arranging ABC, but because they have said order of these letters among themselves does not matter, so it will be done in just one way. So this becomes 9 factorial into, I think this is 120. 10 into 9 into 8 is 120. Yeah, so that will be the answer for this question. Now I can do this question in another method. Please see how this can be done. Let us assume that these 3 letters A, B, C are actually A only, because if their order doesn't matter, then we can consider that they are just same letters A. Then without considering that they are together or not together, if I do the arrangement, it will be then 12 factorial upon 3 factorial, because these 3A are alike and these 9 digits are different. Now I have to subtract those cases in which 2A are at one place and 1A is at other place. In this case, we will be having 9 digits, 2 such letters, so it will be done in 11 factorial. 9 plus 2 is 11 factorial, because these 2A and this A now have become different, so no division by any factorial is required here. But please understand, there will be instances when 2A here and A here will be together, then actually they will form a group of 3 A's together. Anyways, we have to subtract that also, but please understand, this can happen when this block is coming first and this block of A is coming later, or it could have been otherwise also. So you can see these two things will be counted twice in this 11 factorial, but actually they will be catering to the same situation A. That means we have actually over subtracted this case, so we have to add one of that case in which all A will be together. So I'll be adding that case in which 9 single digits and 1 this A block, so that will be 10 factorial. Let us see whether we are getting same answer or not. 12 factorial upon 6, I can write this as 2 into 11 into 10 into 9 factorial. 11 factorial I can write as 110 into 9 factorial plus 10 into 9 factorial. So if you check, I think this will be 220 minus 110, 110 plus 10. So 120 into 9 factorial is the answer from this way also. In fact, you can write this as 12 into 10 factorial. 12 into 10 factorial. So this second method, let me tell you, this is in this method we are able to do this question because there were just 3 letters. If number of letters would be 4 or 5, then this method will become increasingly difficult. Whereas this method 1 is better, and it will be, it can be applied to any such questions. It's a very standard problem. Whenever we have to keep any one type of objects separate, then we find a number of gaps, and that way we will be doing it. Okay. Now coming to next question, number 2 for this question only. Find number of functions from n to L such that exactly 3 numbers are mapped to each A, B, and C. That means we want A should be connected with 3 elements, maybe 1, 2, 3. B should be connected to 3 elements, maybe 4, 5, 6. And C should be connected to also 3 elements like 7, 8, 9. But that was just one example. In how many ways we can do it, please understand. To do this question, I think we just have to select first 3 elements in 9C 3 ways, which will be connected to A. And then from remaining 6, again we will be selecting 3 more elements that will be connected to B. Okay. And then we will be selecting 3 more elements in 3C 3 ways that will be connected to C, and that is the answer. If you simplify it, we will be getting this as 9 factorial upon 3 factorial power 3. This question can be done with group formation also. What we have to do, we have to create 3 groups, each having 3 elements. So here 9 objects, all the groups of 3 objects each will be 3 factorial, 3 factorial, 3 factorial. And because all the groups are of same size, so additional 1 upon 3 factorial will be done. But then these 3 groups will be distributed to A, B, C. So which one will be going to A, which one will be going to B, which one will be going to C. So we can multiply this in 3 factorial ways. So hence we are getting 9 factorial upon 3 factorial cube. So this way also you can see same answer we are getting. Now coming to third part of this question, in which we are asked number of onto functions from n to L. Now for this question again we may have 2 methods. One is inclusion exclusion method, in which we will first count all these functions. All these functions means when 1 to 9 these elements are connected to either A or B or C. So every element here is having 3 options. So 3, that will be 3 power 9. But in this case we have to subtract those cases in which, let us say, A is not connected, or B is not connected, or C is not connected. So who is not connected, that we will be selecting in 3C 1 ways, and then these 1 to 9 elements will be connected to the remaining elements in 2 power 9 ways. But in this case, when we are leaving A, we are not connecting any element of n with A, and we are connecting all elements with B and C. There are chances that B may remain empty or C also may remain empty, because we are doing 2 power 9 without thinking that whether every element is going to B itself or going to C itself. So here there will be cases when we have actually counted here in which A and B are not connected to anyone, C is connected to all the elements. And you can see this can happen then also when B is not connected to anyone in the beginning, and later A was also not connected and all the elements went to C. So please understand this case in which all elements are connected to C in this calculation are actually counted twice. So we will be adding those cases in which 2 elements, maybe A and B or A and C or B and C, are not connected, and all elements are connected to the remaining third element. This is nothing but inclusion exclusion principle. We could have done it directly also. So this will be the answer for this question. You can simplify it, but I think 3 power 9 is a very big number. 3 power 6 is 729. 3 power 3 is 27. Minus 2 power 9 is, I think, 512. 512 into 3. I think that will be 1536 plus, I think, 3 here. So that will be the answer of this question. We can calculate it, or maybe we can leave the question, leave the answer here also, because the purpose here was that how you do it. Answer can be calculated. Now what other method could be? Please understand, method 2 for this third part could be using group formation once again. See, here we want all the elements of n should be given to L so that no A or B or C goes empty. So we will have to distribute these 9 elements into 3 groups of size maybe 1 plus 1 plus 7. And then one group will go to A, one group will go to B, one group will go to C, or we can do 1 plus 2 plus 6, or we can do 1 plus 3 plus 5, or we can do 1 plus 4 plus 4, or maybe we can do 2 plus 5, or 2 plus 3 plus 4, or we can do, I think last one would be 3 plus 3 plus 3. Now for every one of them, we have to make the group and we have to distribute to A, B and C. And how it is done? For first group, you know, it will be 9 factorial upon 1 factorial twice. There is no need to write 1 factorial, but because two groups are of same size, so additional 2 factorial will be divided here. Plus for second one, it will be 9 factorial upon 2 factorial, 6 factorial. For third one, it will be 9 factorial upon 3 factorial, 5 factorial. Plus next would be 9 factorial upon 4 factorial 2 times, but because two groups are of same size, so additional 2 factorial will be dividing it. Similarly, 9 factorial upon 2 factorial square into 5 factorial, plus 9 factorial upon 2 factorial, 3 factorial, 4 factorial, plus 9 factorial upon 3 factorial 3 times, and because all groups are of same size, so additional 3 factorial will be multiplied here. And these are the total number of groups that we can form, so that every group will be having at least one element, and this will be then multiplied with 3 factorial, and it can be checked that we will be getting same answer whether we do this way or that way. But I think this is better way, not this one, because so many number of groups we have to create. Okay, so this question I will say was easy. In JEE PNC we do such questions very frequently, so not very difficult question, I will say. Now coming to question number 2, we are given that function f from natural number to natural number that satisfies fn is equal to n minus 2, and f of n is also equal to f of n plus 5 for n less than 3000. Earlier one was for f greater than 3000. Okay, now we have to prove that f 2022 is uniquely decided, and we have to find its value. So I'll be first telling you how f 2022 is calculated, and this same method can be used to find any value of can be used to find f at any value of n, although that is not required here. So here please see what I am going to do. F 2022 using this second one, because n here is less than 3000, so I can write this as f of 2027. So here f was just once. Now f of f, it is here f repeating 2 times. Now once again, if I use this same thing, okay, we will be getting this to be equal to f of 2032. And in this case, f is appearing 3 times. Now everybody please see, if I keep on doing this way and just wait, have patience, I think this will give you answer directly. If you keep on doing this way, you can see the number here is actually forming an AP. Okay, first when f was appearing once, it was 2022. Then when f was appearing 2 times, it is 2027, and so on. You can say first term is 2022, second term is 2027, third term is 2023, and so on. If I keep on doing this way, I think f of I think last one would be 3002 actually before that there will be that would be 2097, but here also we will be able to use this formula, but then it will become f of 3002. Okay, now we have to count how many times f are here. See here this AP, if you count, its common difference is 5, so its general term would be 5n plus 2017, and here 3002 if we are getting, so 5n will be equal to, we will be subtracting it, so 12 minus 7 is 5, 9 minus 1 is 8, and here also I think it would be 9. Okay, so here you can see this n will be equal to 1, 9, and I think 7. Yeah, 197. So here this f will be appearing 197 times. Here it would have been 196 times. Now after that, as you can see, we cannot apply this result because it was only for n less than or equal to 3000. But here I can use the first one, in which 3002, because n is greater than 3000, I can write f of 3000. In this case, you can see 1 f of 3002 will be written as 3000. So here appearance of f will be just 196 times. Now once again, for n less than or equal to 3000, if we do it, we can again write it f of 3005. And in this case, this f will be once again written 197 times. Now, if I use this formula greater than 3000, so once if I use it will give you f of 3005 as 3003. F 3005 will be 3003. And once again, if you use it, so f of 3003 will be 3001. And once again, if I do it, it will be 2999. And then we cannot use this formula. So here you can see I will be using f of f 3 times, and we will be getting f of 2999. In this case, 3f would have been reduced, so it will be just 194 times. Just have patience. We are just about to do this question. Now after that, I think this formula will again be valid. So we can write this as f of, and it will be 3004. And in this case, f will be, would have increased its occurrence, and it will be 195 times. Now once again, we will be using the first one, and in this at this time, this will be giving you f of 3002 and then 3000, and the appearance of f would have decreased by 2. So here we will be getting 193 here. Now you can see we got f of 3000, in which f was appearing 196 times, and here once again we are getting f of 3000, in which f is appearing 193 times. Now I think we can assume it that same process will follow, and next time when I will be getting once again 3000, this f of this appearance would be, I think, 190 times only. And similarly, if we keep on doing, this appearance will reduce by 3 every time. Okay, and 190 when divided by 3 gives us remainder 1. So here in the end, I can say it will become f of 3000, where f is appearing only once. Okay, now for 3000, we can again use the second formula. So this will become f of 3005. And then we will be getting f of 3003 first, because we will be using the first result, and then we will be getting 3001. Okay, so here I have proved it for 2022, but this method, actually this difference of 3 is a very critical thing, that when you are reducing this f appearance of f by 3, we will be getting same number here, and this 3000 is for 2022. For other number it can be maybe 3001 or maybe some other number. So going with that pattern, we will be able to prove that for every number we will be getting a unique number, and we can find that also. Okay, in fact, using congruence modulo, we can tell that for which number n in general, what will be the formula for that. But for now, I think this question, I think we can conclude here itself. So answer is 3001, and I will say this was a good question. Okay, now coming to next question, in which we are given triangle ABC. This BAC is equal to 2 times ACB. 2 times ACB. That means this angle A, that's a standard terminologies in triangle ABC. Angle A is equal to angle 2 times angle C. So this A is 2 times C. And this angle BAC, that means angle A only, that is less than 120. And obviously it has to be greater than 0 because it is forming a triangle. A point M is chosen in the interior of triangle ABC such that this BA means it is C, small c, is equal to BM. Okay, and MA, this length, is equal to MC. Prove that this MCB angle is 30 degrees. So we have to prove this angle will be equal to 30 degree. Let us see how this question can be done. So here, if A is equal to 2C, we can write all the angles in terms of C only. Like A is 2C, so B will be equal to 180 degree minus A plus C. That means it will be 180 minus 3C. Okay, so that is one thing. Now, if this angle is X, I think this angle will be X minus C minus X. And because these two are equal, so this angle will also be C minus X. Okay, and this complete angle here is A, which is 2C. So I can write this angle to be equal to 2C minus this. So that will become C plus X. A is 2C, so 2C minus C minus X, so C plus X here. Now, because these two sides are equal, this BM and BA, so if I drop a perpendicular from B to AM, it will meet at its midpoint. Similarly, from M, if I drop a perpendicular, it will also meet at the midpoint. Let us call these midpoints as, let us say, P here and Q here. Okay, now I can use simple trigonometry and I will be getting that cos of C plus X in this triangle APM, APB, that will be equal to AM by 2 as numerator upon C. Okay, so that is AM upon 2C. That is one. Similarly, in this triangle AMQ, if I use, we will be getting cos of C minus X is equal to, that will be, and AQ. Yeah, and this AC complete length will be B. So B by 2 here and B by 2 here. So we will be getting B by 2 here and divided by AM here. So B upon 2M, 2 times AM. Now, if I multiply these two equations, and cos C plus X into cos C minus X means it will be cos square C minus sin square X. And that will become, I think AM will be cancelled and we get B upon 4C. Okay. Now I will be using B upon C using sine rule. So B upon sine B will be equal to C upon sine C. And because B is 180 minus 3C, I can write B upon C as sine of 180 minus 3C means sine 3C upon, here it will be sine C. So this will be 3 minus 4 sine square C. Okay, or let me write this in terms of cos. So then it will become 3, that will become 4 cos square C minus 1. 4 cos square C minus 1. So we can write here this as B upon C is this. So dividing by 4, we get cos square C minus 1 upon 4. So if you see on the left hand side cos square C and right hand side cos square C will be cancelled, and we are getting sine square X is equal to 1 by 4. And this has to be positive only, so 1 by 2. And also this angle cannot be 150. It has to be 30 degree only, because we are given that this angle is less than 120. So X is equal to 30 degree. So this completes the solution of this question. See, this question is, I will say, moderate plus level, because you cannot believe that these steps will give you answer ultimately. Most of the people think of some geometry or some other methods also, but I think mostly geometry people will be trying here. But I think this one was better. This one was better because simple trigono we have to use, nothing else we are using here. Okay. Coming to question number 4, it says we want to find a non-zero polynomial px with integer coefficients having the following property, that qx is equal to px upon x into 1 minus x, and qx also equal to q times q of 1 upon 1 minus x for all x not equal to 0 and 1. Find one such polynomial with smallest possible degree. Find one such polynomial with largest possible degree, or show that degree of such polynomials is unbounded. Let us see. So we are given that qx is equal to q of 1 upon 1 minus x. If I use this and use this relation also, we will be getting that px upon x into 1 minus x, and on the right hand side it will be p of 1 upon 1 minus x whole divided by 1 upon 1 minus x into 1 minus 1 upon 1 minus x. Okay, this after simplification becomes p of 1 upon 1 minus x upon, I think, minus x if we take LCM here, and upon 1 minus x whole square here. So if you do the cross multiplication, I think first this x will be cancelled. Already x is not equal to 0, so we can cancel it here. And if I do the cross multiplication, we will get px is equal to minus of 1 minus x whole cube into p of 1 upon x, p of 1 upon 1 minus x. Now taking 1 minus x as t, we will get x as 1 minus t here, and this will give us p of 1 minus t is equal to minus of t cube into p of 1 upon t. Now please understand, this is one very important relation here, though I could have concluded same thing from here also, but here you will find it better to understand. Please see, this p of 1 minus t has to be a polynomial, because p is a polynomial, so p of 1 minus t will also be polynomial, because we are replacing x by 1 minus t. But here, if p of x is polynomial, p of 1 by t will be polynomial in 1 upon t, but not in absolute sense. We will be getting negative power of t, and it is multiplied with t cube outside. So in order this left side to be polynomial, and hence this right side should also be a polynomial, we will require that this t cube should cancel all the negative powers of p, so that right side is also a polynomial. So here degree of p can be at most 3, because if it is 4, then t cube will not be able to cancel that 1 upon t power 4 term. If degree is 4, you will be getting 1 upon t. On the left hand side we cannot have, so degree will be at most 3 here. Please understand, so either degree can be 1, or degree can be 2, or degree can be 3. So maybe that is what they were asking, find one such polynomial with smallest possible degree. So with smallest possible degree, I'll write this equation once again here. We got that p of 1 minus t is equal to minus t cube into p of 1 by t. Let us check once again. Yeah. Now if degree is 1, let us say degree is equal to 1. So in that case, we can take p of t to be equal to some at plus b. Putting it in this equation number 1, we will be getting here a times 1 minus t plus b. On the right hand side, it will be minus t cube into a upon t plus b. And because if degree is 1, a cannot be equal to 0. And you can see here on the right hand side, there is a term of t square also. You can see it is minus at square plus bt cube, minus bt cube actually. Maybe I could have said that b will be 0, so t cube term will not come, but this t square term will definitely come. But on the left hand side, we are not having such higher degree term, so I think this is not possible. So degree 1 polynomial is not possible which can satisfy this result. Now we will next take degree to be 2. Actually this is directly visible also, that if someone takes px as x into 1 minus x, or some constant times x into 1 minus x, then qx will become constant, And if qx is constant, q of 1 upon 1 minus x will also be same thing. So it looks like for degree 2 we have to get some solutions. So let us see properly that if degree is 2 and let pt is equal to at square plus bt plus c. In that case, this left hand side will become a into 1 minus t whole square plus b into 1 minus t plus c, and that will be equal to minus t cube into 1 upon t, that will become a upon t square plus b upon t plus c. Okay, so if I open these brackets, it is 1 plus t square minus 2t plus b into 1 minus t plus c, and on the right hand side it will be minus at minus bt square plus ct cube plus ct cube. Yeah, ct cube. Obviously on the left hand side there is no t cube term, so the c has to be 0. Okay, now if I compare, this is because there was no t cube term on the left hand side. Similarly, if I compare t square term, so it will be a here and it will be minus b here. So we will be getting a equal to minus b. Similarly, for t, if I compare, we will get minus 2a minus b, and that will be equal to minus a. Okay, here also I think we are getting same result, a plus b equal to 0. This is same as t square. So if coefficient of t square will be same, I think coefficient of t will also become same on both sides. Now coming to constant term. For constant term, we will be getting here, I think a plus b, and c is already 0, and on the right hand side it is 0. So you can see every time we are getting a plus b equal to 0 only. So in this case I think my polynomial t or pt will be actually a common, as a is equal to minus b. So a common, we can write this as t square minus t, or we can write px is equal to a into x common x minus 1, and you can see it is exactly same as I was telling you in the beginning. It is also same, just minus sign difference is there, but that will be included inside a. So this is first smallest degree polynomial that is possible for this relation. Now coming to next thing, that is when degree will be 3. When degree will be 3, I think we can take pt is actually equal to a into t cube plus b into t square plus c into t plus d. So here this p of 1 minus t from this equation will become a into 1 minus t whole cube plus b into 1 minus t whole square plus c into 1 minus t plus d, and on the right hand side it will be minus t cube into p of 1 by t, that is a upon t cube plus b upon t square plus c upon t plus d. Okay, so here if we start comparing the coefficient, let us do it directly. So for t cube, if I compare, on the left hand side I will be getting minus a, on the right hand side I will be getting minus d. So a is equal to minus d, a equal to minus d, that means a equal to d. So that is one thing. This is from t cube. Now comparing t square, I think we will be getting minus 3a here, plus 3a actually, plus 3a here, plus b here, and on the right hand side we will be getting minus c, minus c. So here we are getting 3a plus b is equal to minus c. Okay, let us write everything in terms of d, or maybe in terms of a. In terms of a, so d is already equal to a. I can write b plus c is equal to minus 3a. So that is one relation I am getting. Here we compared t square. Now let us compare the term of t. So let me write here also, because otherwise it will become a little confusing. This we got from comparing t cube, and then we compare t square, then we compare t square, and we got this, And let us now compare t term. On the left hand side it will be minus 3a minus 2b minus c, and that will be equal to minus b on the right hand side. Okay, so here we will be getting, I think, b plus c is equal to minus the same equation as we got it here. Let me write this here only. We will be getting b plus c is equal to minus 3a. So I think t square and t, they are implying the same thing. Now coming to constant term, if I compare constant terms, so constant term will be a on the left hand side, then b also on the left hand side, plus c plus d, and on the right hand side we are getting equal to minus a, equal to minus a. Okay, let me use next slide. So what we have got so far, we have got here that a is equal to d, then we got b plus c is equal to minus 3a, b plus c is equal to minus 3a, and then we have got a plus b plus c plus d is equal to minus a. So a is already equal to d, so here I can write a plus d. I think once again we are getting b plus c is equal to minus 3a only. Yeah, I think we are again getting the same result only here. Please check, because d is equal to a. So if I take all a on the other side, so we will be getting this. So I think these are the two conditions. So what we need to do, we need just to write that leading coefficient, if suppose it is a, then the term b can be anything, but then the next c will be just minus 3a minus b into t, and constant term will be a only. So that will be the polynomial of 3 degree that is possible. So there are only two possibilities, either a quadratic or a cubic. Okay, and in this cubic, this leading term and this constant term, they will be same. Coefficient of t square and t will be such that their sum is equal to minus 3a. So here, other than this, I think there is no restriction. A, b can be any real numbers. So this will be satisfying this one. Okay, I think this is also a good question. Calculation was required, otherwise there was not that difficult question. Coming to next question number 5. Let R plus denote the set of positive real numbers a 1 to 1 and onto function f r plus to r plus is called golden if f dash x is equal to f inverse x for every x belongs to r plus. Find all golden functions if any of the form fx is equal to a into x power b. Find all golden functions if any of the form fx is equal to a into b power x. In both cases, a and b are suitable real numbers. Show that there is no 1 to 1 and onto function f r to r such that f dash x is equal to f inverse x for every x belongs to r. So for first one, for this thing, the derivative would be a into b into x power b minus 1, whereas its inverse would be x upon a whole raised to the power 1 upon b. See, to find inverse, we just use y is equal to a into x power b. So we get x is equal to y upon a whole power 1 upon b, and replace x and y, we get inverse. Now if I raise power by b on both sides, we will be getting a into b power b into a into x power b square minus b is equal to x. So we will be getting two relations. One is b square minus b is equal to 1. That gives a quadratic b square minus b minus 1 is equal to 0, whose roots are 1 minus 1 plus root 5 upon 2 or 1 minus root 5 upon 2. Okay, one is positive, one is negative. And then comparing the constant term, we will be getting a power b plus 1 into b power b is equal to 1. So this gives a equal to 1 upon b power b whole raised to the power 1 upon b plus 1. From this equation, b plus 1 is actually equal to b square. So I can write this as 1 upon b power b whole power 1 upon b square, which gives us 1 upon b whole raised to the power 1 upon b. So here this function that is a possibility is fx is equal to 1 upon b whole raised to the power 1 upon b into x power b, where b is given by this. And there is one more thing I will say, that if we take this one, then this base will become negative and power will be irrational. That is not defined. So I think only this root will be taken, 1 plus root 5 upon 2. Okay. Now coming to the second part. Find all golden functions of the form this. So f dash x here will be a b power x into ln of b, and inverse here would be, I think we will be writing y is equal to a b x. So b power x will be y upon a. So this x will be log of y by a base b. So here that will be log of y x by a. Actually we will be interchanging x and y also, and base b. So you can see here we are having log function and here we are having exponential function, so they cannot become equal. So no such function possible. Now coming to second part, it says show that there is no bijective function fr2r, so that f dash x is equal to f inverse x. See, if fx is bijective and it is differentiable also, assuming, because they are saying for all r to r f dash x is equal to f inverse x. So if fx is bijective, and from this given relation f dash x should be defined for all x. So here f dash x will be positive for all x if it is bijective, or negative, but not both. Not both means sometimes positive, sometimes negative is not possible. So either only positive, either only negative. But if bijective, then f inverse x will have range all real number. So either negative values will not be possible for this f inverse f dash x, or positive value will not be possible for this f dash x. So this is not possible. That is what we were supposed to prove. So f dash x equal to f inverse x, not possible. Okay, so this completes this question. Now coming to the last question of this paper. Suppose an integer n greater than 1 is such that n plus 1 is not a multiple of 4. N plus 1 is not a multiple of 4 means n is not equal to 4k minus 1. Such that n is not congruent to 3 mod 4. Prove that there exists this such that the following is a perfect square. Okay, 1 less than or equal to I less than j less than or equal to n such that the following is a perfect square. Okay, so suppose I take n is equal to 4k. Okay, then this expression you can understand very easily that 1 will be appearing in all these factorials. So 1 will be 4k times. Then 2 will be appearing one less number of times, because it will not be there in one factorial, but it will be there in all other factorials. Then 3 power 4k minus 2 and so on. And this last number n, that is 4k here, that will be having power 1 here upon I factorial and j factorial. So here you can see all the odd numbers are having even powers. So here already this 1 power 4k, 3 power 4k minus 2 and so on, 4k minus 1 will be having power 2. Their product will be already perfect square. And then if I write 2 power also like 4k minus 2, and 4 power will be actually 4k minus 3, but I will write that 4k minus 4 and so on. And then 4k minus 2 would have power, I think 3, so I will write 2 power here. So I have actually taken 1 power of each. So 2 into 4 into 6 and so on, 4k. I think this will be going extra. Why I have done so? Because already these two brackets, this bracket and this bracket is a perfect square, and we need to prove that for some ij this can also be made perfect square. So let us write these two product as m square, and then it will be 2 power 2k common because all the even terms are there, and then it will be 2k factorial and upon I factorial j factorial. 2 power 2k is again a perfect square number. So if I take I is equal to 1 and j is equal to 2k factorial, then I think this will become perfect square. Okay, so I think for this n is equal to 4k it is done. Now let us see if we have to do for 4k plus 2 also. Let us do it separately. Suppose I take n is equal to 4k plus 2. In that case, this will again be like that 1, 3, and all they are having even powers only. Let me write completely. So 1 will be having that power 4k plus 2, 3 will be having 4k power, and so on. And the last number 4k minus 1, last odd number 4k plus 1 will be having, I think, 2 power. Yeah, 2. And then again I will be writing the same thing, that take 2 outside, 2 power will be actually 4k plus 1, but I will write 4k. Then 4 will be having 4k minus 1, but I will write 4k minus 2, and so on. And here we will be getting this 4k plus 2, 4k will be having, I think, power 2 here, power 3 here actually. So I will write 2 here, and then all the remaining numbers 2, 4, and so on, 4k plus 2 I will write outside this bracket. Once again I am using the same logic that these two are perfect squares, so let us write that as m square, and here we will be getting 2 power, this time 2k plus 1 common, and we will be getting 2k plus 1 factorial upon I factorial j factorial. So you can see if I take I is equal to 2 and j is equal to 2k plus 1, this will become perfect square, because then this 2 will reduce this power of 2 by 1, so this will be perfect square, and this j is equal to 2k plus 1 if we put, this will get cancelled and we will be getting perfect square. Now the last thing, that is n is equal to 4k plus 1, because 4k minus 1 we are not allowed to take, so 4k plus 1. So in this case what we can say, that this given expression can be written as 4k plus 1 outside, 4k plus 1 factorial, and all those things that we got for the first case, that is 1 factorial, 2 factorial, and so on, 4k factorial. And if you remember, for that I needed I as 1, so let us not write I, let us write j as, I think I needed j to be 2k factorial. So if I take j as 2k factorial, so this quantity will become perfect square, and 1 I factorial is also remaining, so I will take I as 4k plus 1 factorial, or maybe because I is less than j, so I will take I as 2k and I will take j as 4k plus 1. So again this will be cancelled and this is already perfect square, so we have proved that it will become perfect square if n is equal to 4k plus 1. So that's all. Thank you so much. So I hope you will like these solutions. So that is all for now. For now, I'll be starting these sessions little bit later, maybe 2-3 weeks later. But as of now, I have completed all these solutioning part of recent year papers, CMI and ISI. So thank you so much. All the best, bachcho. Take care. Bye.